So welcome back to the arcade ROM hacking series of videos, and this is hopefully, I think, the last one where we're going to show you how to bypass checksums. If you haven't already read the Akari Warriors ROM bypass or free play hack, it's on arcade-cabinets.com. You click on resources and go down to ROM hacking tutorial. Read this, because we're going to use some of this information, just the first part regarding how we did some of this things. So it's going to be easier to show you if you've read this or if you get lost. Basically, just setting a watch point and finding where things change, where a memory address is being located. But anyway, so we'll put that away for now. So okay, so before we get into GHIDRA, we need to find out where this code is breaking, basically when we edit something. So we're gonna go ahead and edit the Akari Warriors ROM. It's in your ROMs. It's your Akari Warriors ROM for ROM Akari. It's 1.rom or 1.bin. It might be if you have an older one. I think it was called, or I don't know. It's the number 1 ROM, basically. So with hex edit, we're going to go ahead and open that up. And we're just going to search for, let's find, yeah. We're going to search for text string, insert, right there, and at offset, where is it? Here we go. AC6, we're going to change that 49 to a 48. Okay, so we actually reduced the value of that by 1. We turned it from an H, an insert, to an I. Okay, so we went from 49 hex to 48 hex. Save it and find out in, we'll start up mame, hit F5, and it shows, there we go, ROM error. Okay, so we want to find out what code actually is accessing that RAM. And I showed you that in that page that I was talking about. That's really the only thing we're going to use about that page. But if you get lost, it helped. And it helps just to read the whole thing. We're going to show you how it's a lot easier with GHIDRA than what we had to do with this. Okay, but we will use the first step. All right, so what we're going to do is we want to figure out what changed here. And basically, we want to find out what accessed this RAM, this address. So we're going to do, the address was AC6, and it starts from offset 0, so it's good. So we're going to do wp set 0xAC6. Actually, let's do help WP. Yeah, FWP. Oh, it's not WP set. It's WP 0xAC6. 1 and read. 1. So it's set a watch point. So when something accesses this memory address, 1 means just it's the range. So we only are looking for this address, and when it's read. And we'll reset it. And there it goes. And we find here that we have address 11686. Actually, though, it's the instruction right before that. So 1185. Remember that address, hex 1185. Okay, that is the one that accessed it, the memory, when it froze. And if we hit F5, continue on, you'll see we get the error right there. All right, so 1185. That's what we need to know. All right. So let's go to 1185. I'm sorry. Let's close this down. I'm just going to move it over here, and I'm going to go ahead and close that down. We don't need that anymore right now. Okay. So I'll go ahead and just close out of that and minimize it. And we want to go to GHIDRA, which I have open up here. And I already loaded the ROM in there. So we want to go to address, so we G for go to 0x1185. And you see a nice little this is called basic blocks. There's 3 basic blocks in this function. And this is it made it very clean C code here. First thing we're going to do is rename this function. We're going to do L for rename. We're going to change this to function where things break. Okay. Function where change was detected. There we go. Okay. So function where change was detected. And actually, I always like to, when I do something, I don't know why, I always like to put a B underscore before it for my name and whatever. That way I know I put that label in there. Okay. And then what does this function do? Well, we have this is a character cvar1 equals 0. Do cvar1 equals cvar1 plus pointer parameter 2. Okay. A pointer is actually just a memory address. And when you say star the memory address, that actually tells you what's stored in that memory. So it's adding whatever cvar is 1, and this looks like it's doing some type of running total. So we'll just call it, and it looks like it's adding. You can see here it's adding. So we'll just call this total. And we'll do a question mark because we're not sure. I always like to put question marks if I'm not sure what something is. So total equals total plus a memory, the value stored in a memory address. Okay. Then it increases the pointer to itself plus 1, so it's increasing. So we're going to rename param2 to, address. Yeah, let's call it address. Okay. And then param3, it says it's pointer to that. So this is the address in memory. So, and then it does param1 equals param1 minus 1, while param1 shift 8. So while param1, okay, so while param1, which is short, which means it's a 16-bit value, and that means the top 8 bits, shifting 8 means we're shifting it right 8 positions. So basically, while there's anything in the top half, the top 8 bits, or the bottom 8 bits are not 0, it's going to keep doing this. And then when it's done, so it's going to keep adding to the value of this total, which looks like a checksum. So let's go ahead and name it checksum, because that actually is what it is. It's a checksum that they get by just adding every number in a memory range. So while that, while we're going to keep adding to the checksum the value at every address, okay? And then when this is done, param3 equals checksum. So it's going to write back the checksum to where it's storing. So this is checksum final value. Okay, very good. Okay. So, and then when it's done, it's going to return. So one thing we can do right here now, we've added some things in param1. This looks like a reverse counter, so I'm going to call this decreasing counter. Okay. And let's see where this was called from. So there's a couple things we can do. We can right-click on references, find references, and there's only one call. Okay, that's good. Or we could have also done this. We could have done window function call graph, and we would see, what called it and what calls that, and so forth and so on. So the path that it took from the start. This is actually the beginning of the program to get there. So I went through this function func_ram 0 dd5 to here. Okay, we want to look at that. So we're going to go ahead and get to that. So I'm going to go back to references and click on it. And we're just going to call this, what are we going to call this? I don't know. We're not going to call it anything right now. But let's look at the values here. So we have this 4,000 or 4,000 hex, which is I can't think anymore. 16,000 0 and the address of something RAM FCC7. And whenever I see something, even if I don't know what it is, and I think I'm not going to see it again, I always label it. So this, I'm just going to call this address checksum. I'm going to call it G for global, checksum destination. Okay. So if I see it, it will pop out at me again. I'm going to save the work. So let's go click on this again. So we know this is called with the values 4,000 decreasing counter. So let's rename that to 4,000 counter 4,000 decreasing. So dec. And the address was 0. Is it 0? Yep. So let's look at this again. The address here. Okay. So checksum equals checksum plus address. Yeah. So it's going to count from basically 0 to 4,000. And for every value, every memory address in 0 through 4,000 is actually going to be 0 through 3FFF, because you start counting from 0, 4,000 actually isn't 4,000, it's 3FFF. Most people are used to counting from 1, so if you have 10 of something, it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Computers, we count from 0 usually, so it's very confusing. Well, it gets very confusing. That would be 0 through 9, so 10 items is actually 0 through 9 rather than 1 through 10. That causes all kinds of bugs, because people get so confused, and whenever I'm programming something and I'm going back from 0 to 1, I'm like, oh, what number is it? Am I off by 1? It's called an off by 1 error, actually. So anyway, it's gonna add up each of these, and this is we're gonna rename this function because we know this is actually the function that computes ROM1 checksum. And again, I just to B in front of it. Okay. Okay, and it's going to store it at this value here, which we know is actually what address was that? Because it's only called once and it's given a hard-coded address. Let's go back again. Checksum dest was FEC7. So I'm going to go back to that function. I'm going to call it checksum at FEC7, I said? I think that's right. We'll find out in a second. FEC7. All right, great. All right, so we now know that this code right here actually is the one that's computing the checksum. Great, that's very helpful. So let's go back to that value, because at some point something is actually going to have to actually access this value. So now that we computed it, we have to actually check somewhere that the value is equal to something, which is going to have to be hard-coded in the RAM somewhere. So let's look for this checksum dest, and let's just do a reference and see what references it. And there's a whole bunch of things that reference it. Okay, interesting. And 2 things write to it, and 1 thing reads from it. Interesting. Or not 1 thing. 1, 2, 3, 4, 5, 6, 7, 8. 1, 3, 4, 5, 6, 7 things read from it. Let's just click through them and see what's going on here. I don't see any type of, I don't actually see where that's actually accessed. Interesting. Okay. It actually is being accessed there, but I don't see why. Well, let's go back to that references again. See if any of them pop out. Let me. Where are my references? There we go. And actually, what I'm going to do is I'm going to actually make a bookmark here. I'm going to right click and say, where's my bookmark? Oh, where's there it is, bookmark. And I'm going to say checksum dest, so I can find it quickly later if I need to by adding the bookmarks down here. Okay. And oh, I don't want any of these ones, so let's filter out the bookmarks. Where's the filter option? And I just want the notes. The notes are things that we added in there. And there we go. So I always know where that is. All right, so let's go back to here. And we're there. Let's see what references it. How about this next one? Where is it being accessed? Okay. I don't think this is it. I don't think this is it. And that looks, no. We're adding things to it. That's not it. This looks like the same thing. Oh, this looks interesting. If checksum dest is not equal to something else. Interesting. And if we click on that address, we notice that's in the ROM. So it's actually checking the checksum value that it computed against something stored in the ROM. That looks potentially good. So is this the function that we're looking for? Func we want? Question mark? I think it is. So let's see what this is doing here. Okay, so if checksum is not equal to some value, let's see what's stored at that value. That value is CE. Okay, so we go to that address CE, and again that's stored in that ROM. So is this? We'll mark this potential checksum value, and I'm going to put the address of it there too, so I can actually remember where it is. Okay. All right. So if it's not, then it sets this. It gets a pointer to memory. What's in that memory? Oh, that memory looks like error. Huh. This is looking like it's very possibly what we're looking at. So it's already loading. If that value is not there, it's loading something where error is stored. Okay, and then it's SVAR 5. It just happens that error is 5 characters long. Looking good. If so, write to this address. Oh, you know what? Why don't we see what this is? I think it's writing something to the screen. So let's bring up, restart it. And there it is. Oops, I don't want IDA. No. Where were we? Come on, GHIDRA. Stop being a pain in my butt. I want this back. Okay, so let's go to new memory window. And let's put in that address, FB6F. That's somewhere in RAM. FB6F. And look at this. What do we have here in this thing? It says error. What's on the screen? Error. Let's pop something else in there. Let's pop in 40. Oh, look at that. It's changing. So this is definitely the thing that's printing out the error. All right. So and we keep looking at it. What it's doing is it's actually just printing out each letter. And then it's going to do while true loop. And that's exactly what the code does. It's actually, if you see here, 1B8, it's just looping to itself. It's doing nothing but, once it writes at the screen, literally nothing. So we have an instruction that just jump to itself. That's definitely the code we're looking for. So now we know that this is the code that prints, or that checks the verifies ROM is not corrupt. Okay, so this is the function we want, and we're going to actually bookmark this too. Okay, function that verifies the ROM is correct. So we want to make sure that this never happens, that this statement is never true. The checksum destination value is not equal to the value stored in ROM. We want to make sure that's never true. So we could do a couple things. We could just modify it so that it never happens. And that's what we initially did in a way back when we did the original hack here. But we would it would be nice if we actually could use that check to make sure our code's not wrong. So rather than doing that, why don't we just replace this value? The value at here, okay, 1708 is CE. Well, we know the algorithm that it uses to compute this value. It just adds every byte together. Okay, so where were we? The checksum destination is not equal to the value stored at this address, which was CE. Again, we can compute this checksum and just replace this value with what the checksum should be. All we need to do is figure out, change our code. So we've already changed the code. We just now need to recompute the values, add them together, and store that value here. Okay, and that should work, right? But we have a problem. The problem is the checksum itself, once we modify the checksum, we have to modify this. But this actually is part of the checksum. Does that make sense? That is, CE is part of the checksum. So if we modify this, then the checksum itself changes again. So we have this situation where we can't just modify this value because if we modify that value, then the checksum is no longer valid. And there's only one condition where that checksum would be valid, is if everything was 0. If the checksum just happened to be 0, then we could actually store a 0 checksum here, and then it'd have no effect. Everything would work. But it's going to be basically impossible to alter our checksum such that it's 0. I mean, it wouldn't be impossible. We could do it. So that leads you back to the question, well, how does the people who wrote the code ever get that checksum in the first place? Because they have to compute the checksum and store the value, but the moment they store the value, the checksum changes. So you have like kind of a chicken and the egg situation. What happens is you need another byte. You need another byte of memory, okay? That you can modify, and that byte, the whole purpose of that other byte of memory is to undo the actual checksum storage value. Because let's say if we have a checksum of 5, okay, we have a checksum of 5, and we want that to store that here rather than CE. Say that all the code is equal to 5, we want to store it at CE. Well, if we put 5 there, then the checksum actually is changing because it's now 10. Because we changed, well, in that case, it's actually not going to be that. Let's imagine the checksum value is 0, okay, initially, because we don't have a checksum yet. So the checksum value with everything stored is 5 when we compute it. Then we go to modify this value, which was, again, starting from scratch, it would be 0. So we add 5 there, but now the checksum actually becomes 10. So no matter how much we change this, we can't get around the problem that the moment we alter the checksum storage, where the actual value that we want to check against, we modify the actual value that the checksum is going to be. So we need a way of undoing this. We need to actually remove 5 from the value. So there has to be another value somewhere where that actually can remove 5. So how do we figure that out? Well, let's figure out how you would do that. One of the things you'll notice is that checksum adds every address of memory, all 16,000 some, and it always has a value though that is only 8 bits, that is of 0 through 255. What's happening is it's doing either, you can call it modulus arithmetic. It's adding and then taking the sum mod 256. Or you can just say it's overflowing, and once it hits 256, it's starting over from 0. I'm sorry. Once it hit 256 is effectively 0. So once you hit 256, you're back at 0 again and just starting over. So let's say you had the number 250 and you wanted to add 10 to it. When you add 10 to it, it's not going to be 260. It's going to be, let's say 250 plus 10 is 260. But if we start over at 256, then it's going to be 256 is 0, 256, 257, 258, 259, 250, 10. It's going to be actually, the value is going to be 4. All right. So we have to have a value basically that undoes this so that it all works out. The way we're going to do this is we're going to actually compute we said the checksum value initially was CE. We want to actually do, which is CE, if we get our gnome, or not gnome calculator. Nope, we went programmer. CE in hex is decimal 206. We want to get negative 206, or because it's just as good to add to 206 so that it gets to 256, we could also just add whatever it takes to get to 256. All right? And you're going to find out that's actually the same number, believe it or not. So how do we do this? Well, 256, 200 CE, if we write it as binary, or I'm sorry, let me get we'll put this up in the corner. Oh, this could be a long episode. Okay, so WordPad. All right, we take CE. If we expand that out, and let's do that. Let's just make this a little bigger so you can see it. CE in hex is this number in binary. Oh, we have it right here in the calculator. I don't even have to compute it. All right. Okay, that's that number. If you want to turn this number negative, and we'll just say this is 250, this is 206 in decimal because it is. So we want to actually figure out what negative 206 in decimal is and store that number somewhere. Okay, somewhere where that's actually not part of the code. All right, so how do we do that? Well, to change a number from positive to negative, you have to flip all the bits and then add 1. So to make it negative, we flip all the bits. So this bit becomes 36. Let's just do this. 36 would be 0011, 0001, okay? And then we have to add 1. So that becomes 0011, 000, nope, that number. If we put that number in our calculator, let's say binary 0011, 0011, that is the number 50 in decimal, which makes sense. 206 plus 50 is 256. That would make it 0. Or hex 32. So let's look to see where the memory, because that means that the programmers had to store that value, hex 32, somewhere in memory, such that everything equals out. And then we just have to, that's the location we can also modify. All right, so how do we do that? Well, let's look at the code again and see if we can use GHIDRA to search for the, what? Wait, this is the number right here, CE. The number directly in front of it is that number. That's too good to be true. That's got to be it, and it is. This is the number that actually nullifies the checksum storage number such that everything works. So we have to change two numbers. We have to change this number and then this number. All right? Well, we know that we just subtracted 1 from the original value that we changed was we turned an I from insert to an H. We subtracted 1, okay? That was just only one letter away. Remember, we did that. It was, where was that value stored? Was it AC6, I think? Let's go to the memory window and go to 0x8 AC6. Yeah, AC6, we changed that from 49 to 48. A, B, C, D, F, G, H, I, yeah. So we just changed that value by 1 digit, okay? So let's just go ahead here and change the address at offset 1708. We'll change that to CD from CE, okay? And we'll go ahead and close that down here. So we're gonna have to reload it. So if we go to 0x1708, we have CE, let's make it CD, okay? We've just changed the value, yay, everyone's happy, right? Almost. Again, if we just change this value, that's not gonna work because the new checksum we compute is now, because we changed two values, we changed the checksum value, which actually is kind of like a recursive problem. It's still not going to work. So let's just verify that. It's still not, even though we subtracted 1 from the checksum value, we still have an error. That's because we also need to modify that other number that subtracts out the checksum value. So let's go there, and that was actually literally 1 byte before that. Here it is. CE was 32. All right. So let's recompute it now. You can say, well, I subtracted 1. That probably means what? You have to add or subtract 1 from here. Well, let's figure it out. And the answer is yes. You're 100% right. But let's figure it out. It's a good practice. Word pad. So the new value is going to be CD. That's what we want to hit. Okay, that's what all the checksums that's what it should be. And CD is that number. D is A, B, C, D. C is 13, which would be right? Yeah, that's 13 in hex. So let's flip the bits. Then add 1. And you could just, if you don't know how to do that math, we can just do this. Again, we can do hex. We can put it in the binary 0011. Actually, I'm just going to make sure that CD it's late, and I want to make sure I actually calculated that right. 00 binary 00. Yep, that's right. Okay. So we flip the bits 0011 0010. Let's put that in there. Clear it out. 11 0011. Add 1. Okay. So now we get hex 33. Put that in there, and that is exactly your answer. We subtracted 1, so we have to add it back in basically. All right. Now let's see if that works. Okay, so now you can see how fast that was by using GHIDRA compared to doing it through the mame debugger. You can see, for example, just in GHIDRA, how you were able to see those structures and the flow of the code and the loops and things like that, whereas you couldn't see that with the mame debugger. And you can just go to any memory address and look at see the instructions, and it's very, very powerful. You can check the references. So hopefully you enjoyed that. Now you know how to alter checksums. The key to altering the checksum is defining what the algorithm is. It's usually something like add or XOR. It just takes every byte through a memory address and either adds it or XORs it with the next byte. That's usually. And then you need to find where it's stored, and if you need to find an offset. If the RAM, if the checksum value is stored somewhere else, not in the same RAM, then the problem's easier. I'm sorry, with the same ROM, then the problem's much easier. Anyway, I know there's a lot of people who've been waiting a long time for that video. I wanted to make it 5 years ago, and I never got around to it. And people have been asking me forever to fill in shit, so it's done. Super long episode. Hope you enjoyed it. So take care, everybody.